Lesson number 9, Electromagnetic Testing. Introduction to Electromagnetic Testing. Electromagnetic testing, abbreviated ET, is an NDT method that uses a variety of techniques to detect surface and near-surface discontinuities with electrically conductive materials. The primary techniques that encompass electromagnetic testing are eddy current testing, alternating current field measurement, and remote field testing. The distinctive nature of each technique stems from differences in excitation frequencies, the nature of the transducers used, and the signal analysis techniques for characterizing the state of the test object. Eddy current testing. Eddy current testing is the most common electromagnetic testing technique. The process uses a magnetic field to induce circularly shaped currents, called eddy currents, into the test piece. These currents are affected by fissures, constrictions, and other discontinuities in the test object. This technique is also used for detecting the wall thickness of thin materials as well as measuring localized discontinuities. Alternating current field measurement. Alternating current field measurement, also known as ACFM, involves the induction of a locally uniform current into a test object and measurement of the magnetic flux density above the test object's surface. It was originally designed for the detection and sizing of fatigue cracking. Remote field testing. Remote field testing, or RFT, can inspect regions not only near the probe but also throughout the thickness of the material. A major application is the testing of thick-walled ferrous tubing, where RFT shows equal sensitivity to internal and external discontinuities. Electromagnetic testing basic principles. Electromagnetic testing of electrically conductive materials is performed using induced alternating current, or AC, reversing at a high frequency. These currents in turn produce alternating magnetic fields. When brought in close proximity to conductive materials, the alternating magnetic fields generate an electrical current in the conductive material. These electrical currents are circular in shape and decrease in area and strength as they penetrate into a test object in the shape of a funnel. The funnel shape of these currents resembles swirling eddies found in rivers and streams, hence the name eddy currents. The eddy currents generate a magnetic field in opposition to the magnetic field that produces them. Electromagnetic induction. During eddy current testing, electromagnetic induction takes place when the coil introduces a changing magnetic field into a test specimen. Once the magnetic lines of force enter a conductor, electromagnetic induction occurs, and a secondary current is generated in the test object, which in turn generates a secondary magnetic field in the part. Magnetic fields. One of the keys to understanding the theory and practical application of eddy current testing is to understand the interaction between the primary and secondary magnetic fields that are generated. The primary magnetic field is generated in and around the coil of the eddy current system, and the secondary magnetic field is generated in the test specimen. By monitoring the effects between the primary and secondary fields on the display, the inspector can differentiate between material properties and discontinuities. Skin effect. Alternating current field measurement uses the principle of skin effect, which allows for alternating current to flow along the surface of a part being inspected. If the part is homogeneous, the current will flow in a uniform manner. Because the current is alternating, there is a magnetic field associated with the current. The presence of any discontinuity causes an interruption in the magnetic field, which the probe can detect. Test coils. Eddy current testing uses high-frequency alternating current to generate the eddy currents in a part. Test coils may be configured in small pencil-like probes. Test coils may be configured to fit inside or outside diameter of a tube or wire for inspection. A single coil configuration generates eddy currents and senses any changes which may occur because of discontinuities in the part. Other configurations, such as one coil generating eddy currents and a second that senses any changes in the induced eddy current fields, may be used depending on the configuration of the part and discontinuities to detect. Eddy current testing theory. Eddy current testing is based on the principle of electromagnetic induction. This principle is applied through a multi-step process. 1. Alternating current passes through a conductor, which is wound into the shape of a coil and generates a longitudinal magnetic field. This magnetic field is known as the primary magnetic field or the AC magnetic field. 2. Electromagnetic induction takes place once the magnetic field is placed near a conductive test part. 3. The changing magnetic field generated in the part creates an eddy current in the part. 4. Because the eddy current is constantly changing directions at the same frequency as the current that was used to produce it, it generates another magnetic field. This field is called the eddy current magnetic field or the secondary magnetic field. 5. The two magnetic fields interact with and oppose each other and are influenced by the material properties of the test specimen. 6. Test systems display and analyze the interactions between the two magnetic fields. Effects of fields created by eddy currents, impedance changes. Alternating current, direct current, and eddy currents all have one thing in common. They flow through the path of least resistance. Impedance is defined as a total opposition to current flow through a conductor based on the sum of the factors in eddy current testing of resistance and inductive reactance. Impedance changes can be caused by numerous factors within the part, including conductivity, permeability, mass, homogeneity, frequency, magnetic coupling, meaning the lift-off or fill factor, field strength, and test coil size and shape. Effects of impedance change on instrumentation. The effects of these changes on the instrumentation display are dependent on the type of display, but the basic premise remains the same. In simple terms, eddy current instrumentation is based on a bridge circuit as shown here. The electrical signals are balanced between the inductor, meaning the coil, which is placed on the part, and an internal variable resistor or external reference coil. When there is a difference between the inductor and the reference coil, the signal takes the path of least resistance, which is where the display instrumentation is housed. This change is in turn displayed in one of the following formats: calibrated meters, impedance plane displays, being either analog or digital, data recording systems, alarms or lights, numerical readouts, marking systems, sorting gates and tables, cutoff saws or shears, automation and feedback loops. The primary format of traditional NDT utilized in industry is the impedance plane display, which will be discussed later. Properties of eddy currents. Eddy currents travel in circular direction and are named for their shape, which is similar to swirling currents of water in a stream. The term eddy current means to move in a circular motion. Eddy current intensity. Eddy currents are strongest on the surface of a test material and are also cyclonic in shape. Their intensity exponentially decays until reaching a point where their strength is no longer usable. Surface breaking discontinuities will disrupt the greatest amount of eddy currents. Eddy current depth of penetration. The depth at which eddy currents travel is based on frequency, conductivity, and permeability. Once the strength of the eddy current intensity reaches approximately 37% of the surface intensity, the field reaches its standard depth of penetration. Once the strength of the eddy current intensity reaches 5% of the surface intensity, the field reaches its effective depth of penetration. Additional factors. There are other additional factors particular to eddy currents. For instance, intensity and phase relationships can vary based on coil parameter and test part characteristics. Also, based on material properties such as permeability and conductivity, the intensity and effect on the magnetic field affect the strength and phase relationship of the eddy currents. Eddy currents also have a small magnitude of current flow. These minor changes can be detected by the inspection system. As with magnetic particle testing, an increase in the current has a direct effect on the strength of the magnetic field and the number of lines of force generated that will be used for the electromagnetic induction. Phase lag. In addition, there is a relationship between frequency and phase. Phase lag means that as the depth of the crack detected increases, the lag of the signal shifts in time on the display. Frequency is the only variable the inspector can change. Higher frequencies result in less penetration of the eddy currents. When choosing a frequency, it is recommended to choose a frequency that provides the penetration and sensitivity desired for the inspection being performed. Parts that have a higher conductivity result in stronger eddy currents. Because of the ease in the flow of electrons in the material, the stronger the secondary magnetic field that is generated, which in turn provides greater sensitivity of the inspection, but also has less penetration in the eddy current field because of the skin effect. The lower the conductivity in materials, the weaker the secondary magnetic field that is created, and the greater the eddy current penetration. Parts with high permeability will result in strong magnetic fields and strong eddy currents. The stronger magnetic field will cause the eddy currents to stay near the surface because of the increased skin effect. When inspecting ferromagnetic materials, the depth of penetration is limited to near-surface or surface inspections. Geometry issues associated with eddy current testing. There are geometry issues present when performing eddy current testing, such as when inspecting thin materials. If the effective depth of penetration of the eddy currents penetrates the total thickness of the material, false indications can appear. Additionally, the inspection of thin materials can be enhanced by increasing the frequency to ensure that the eddy currents terminate in the material. Another geometric issue is when inspecting near edges. Eddy currents get confined when approaching an edge and cause a change in the impedance of the coil, which can look similar to a discontinuity. Eddy current applications. Eddy current systems can be utilized beyond discontinuity detection. Eddy currents are useful in determining the state of a test specimen's material properties, including changes in conductivity and/or permeability caused by a change in the part's temperature or hardening. Additionally, eddy currents are able to detect changes in conductivity due to parts subjected to localized overheating. Typically, the primary purpose of eddy current testing is to detect discontinuities such as cracks, inclusions, gouges, and other surface and near-surface imperfections that could affect the serviceability of a part. Finally, eddy currents are also a useful tool to detect changes in the geometry of a part, such as measuring back wall surface corrosion, which can cause thinning of material. Advantages of eddy current testing. Inspections are fast. There are no hazardous materials. There is little operator danger, and they are sensitive to small discontinuities. Limitations of eddy current testing. The scan areas are very small. They are limited to surface and near-surface testing, especially in ferromagnetic parts. There is a high level of experience needed. Types of eddy current sensing elements. Eddy current sensing elements refer to probes and the type of coil arrangements. Also known as surface probes, probe coils are typically used to inspect plates or sheets and are used heavily in the aviation industry to inspect aluminum aircraft skins and support structures. Encircling coils are coils circular in shape used to inspect the outer diameter of rods and tubes. They are used heavily in the manufacturing industry to inspect production parts. Inside coils, on the other hand, are coils designed to inspect the inside diameter of tubes and pipes and are used heavily in the petrochemical industry to inspect heat exchanger tubes. Modes of operation. Absolute. Used to interrogate directly under the coil and uses one coil to both create the magnetic field and detect changes in the secondary magnetic fields. Differential. The differential coil design uses two or more coils and compares one area to another either in one housing or in separate housings with a separate balanced coil on a separate standard. Hybrid. Can be in different forms, but a common technique is through the use of a driver coil and separate pickup coils. It is also known as the reflection mode. Array probes. Consist of coils arranged in different shapes to allow for large area scans through the use of multiplexing coils to eliminate the effects from mutual inductance. Hall effect sensors. Primarily utilized in the magnetic flux leakage testing method and are used at low frequencies in comparison to traditional eddy current tests. Factors affecting probe selection. The type of part and the surface areas to be inspected dictates the type of coil design. For example, when performing a surface inspection on a small area, a traditional surface probe would suffice, whereas if inspecting a large area, an array-style coil design would be more effective. When inspecting rods, the inspector would choose an encircling coil, and when inspecting a tube, the inspector might choose an inside bobbin coil. Additional factors that affect coil selection include the testing speed, the sample size of the inspection area, and the location of the expected discontinuity. The closer to the edge of the part, the more the impedance of the coil will be affected by the edge effect. This constricting of the eddy currents can often be misinterpreted as discontinuities. Types of detectable discontinuities. The types of processing and manufacturing discontinuities that can be detected with eddy current testing include but are not limited to rolling, forging, and extruding, forging laps, hydraulic tubing, inclusions or stringers, mandrel drag, seams, tubing cracks, welding, arc strikes, and surface shrinkage cracks. The types of surface discontinuities that can be detected with eddy currents include, but are not limited to, fatigue cracks, intergranular corrosion cracking, stress corrosion cracking, and thread cracks. Selection of inspection parameters. The frequency. Frequency affects the effective depth of penetration. As frequency increases, it results in loss of depth of penetration, but greater sensitivity at the surface because of greater skin effect of the current flow. Choosing the optimum frequency provides the greatest signal output while maintaining the appropriate depth of penetration. Coil drive. Coil drive increases the strength of the magnetic field, but has no effect on the depth of penetration of the eddy currents. Generally, lower signal amplitude is required with a higher coil current because of the strength of the magnetic field generated. Gain. Gain is a signal processing circuit that has no effect but to increase both wanted and unwanted signals. Display sensitivity. Most units have the ability to input either vertical or horizontal bias to increase the probability of detection of the area of interest from the areas of non-interest. Standardization. Standardization of the signal to a known discontinuity size and location is critical for correctly categorizing discontinuities. Filtering. Using both high-pass and low-pass filters can allow the inspector to create a band of usable signals and remove or suppress unwanted signals. Thresholds. Thresholds, also known as gates, can be utilized to alert the inspector when a signal has surpassed a set parameter. This is traditionally set up as an amplitude threshold, but can be set up to detect phase changes as well. Displays. There have been numerous types of displays over the course of development of eddy current systems. However, typical displays in modern systems are based on impedance and impedance plane analysis displays. The original displays were based on an analog meter. Indications were indicated by a deflection in the meter needle. Current displays are digital and show both amplitude and the accompanying phase changes that provide greater information concerning indications and discontinuities. And that concludes this lesson.